So to remind ourselves, we say that y is the modular inverse of x in modulo m if x times y is equivalent to 1 in modulo m. Can someone tell me why that's the definition of a modular inverse? Like, why is y the inverse of x when x times y is equivalent to 1? Like, why is that the definition? Yeah?
Because it sort of extends the idea from just normal integers or like normal numbers that when you multiply a number by its multiplicative inverse, you get 1.
Exactly. This is the same definition that we had with regular integers and real numbers, right? By dividing by n, it's the same as multiplying by the multiplicative inverse of n, right? And how is the multiplicative inverse defined? It's the number such that when you multiply n by it, you get 1. Is that clear? Right? So to solve, I don't know, let's say, same examples before, 3x is equal to 14. By dividing by 3, I'm effectively multiplying both sides here by the multiplicative inverse of 3. Right? And that's 3 times this inverse gives me 1, and that's how I get x is equal to the inverse of 3 times 14, which in regular arithmetic is just 14 over 3. Any questions with that? So that's why the inverse of x is defined by some number y, such that when you multiply x and y, you get 1 in modulo n. Cool. So for example, the inverse of 3 in modulo 5 is 2, because 3 times 2 is 6, but in modulo 5, that's equivalent to 1. So we say 3 is the inverse of 2, and 2 is the inverse of 3. Is that clear? Cool, yeah.
So it would be like equivalent that 2's inverse is 3.
Yeah, because 3 times 2 gives you 1, and 2 times 3 also gives you 1. Cool. However, as you see, or as we looked at last week, the inverse of 10 in modulo 12 does not exist. Okay, because there's no solution to 10x is equivalent to 1 in modulo 12. And as we saw last week, we can rewrite the problem of finding the inverse of a in modulo m as finding integer solutions to the equation ax plus my is equal to 1, where this will help us find the inverse of a in modulo m, right? And here, x is the inverse of a in modulo m. Okay, so if we're able to find integers x and y that satisfy this equation, we know that x is the inverse of a in modulo m. Is that clear? So for example, going back to the problem of finding the inverse of 3 in modulo 5, I can write this problem as finding integer solutions to 3x plus 5y is equal to 1. And at this point, we didn't know the extended Euclidean algorithm, so we just sort of had to guess and check. And we saw that if you plug in 2 for x and negative 1 for y, the equation holds. And that tells you that 2 is the inverse of 3 in modulo 5. Is that clear? Because 2 was the value we found for x. Right? So we can rewrite this problem of finding the inverse of a in modulo m as finding integers x and y that satisfy ax plus my is equal to 1. And that showed us why, in the case of finding the inverse of 10 in modulo 12, there's no solution, right? Because I can write 10x plus 12y is equal to 1, but since the greatest common divisor, right, i.e. the largest factor that is a factor of both 10 and 12, which in this case is 2, right? The GCD here of 10 and 12 is 2. Since they both share that factor, I can divide it out on both sides, and I'm left with this 5x plus 6y is equal to 1/2, right? But I know I'm trying to find integers x and y, but 5 times some integer plus 6 times some other integer will always be another integer. So it's impossible for it to be equal to 1/2, which tells us that when the greatest common divisor of a and m is anything other than 1, there's no inverse of a in modulo m. Is that clear? So any questions with that idea? Okay, so again, to repeat what we've covered, finding the inverse of a in modulo m is the same as finding some integers x and y that satisfy ax plus my is equal to 1, where x is that inverse. And we see that this inverse only exists when the greatest common divisor of x and m is 1. Sorry, that's a little confusing. In this slide, we're using x to refer to the number we're taking the inverse of, but here we're referring to a as the number we're taking the inverse of. But either way, what we mean is that the GCD of a and m has to be 1. Yes?
What is y supposed to represent?
So when we're trying to find solutions to the equation, ax is equivalent to 1 modulo y, right? Or 1 modulo m. So y is just the factor, y is the multiplier on m that tells you, I guess you can say it as y tells you what factor of m a times x is 1 away from, if that makes sense, right? Because we're finding solutions to ax plus my is equal to 1. Y is just tells you which factor of m it's 1 away from. Is that clear? So in the problem of finding the inverse of a in modulo m, y itself it doesn't really factor into the solution. But you need to find solutions for both x and y for this story. Yeah.
On the lecture slides, you showed multiple ways where x and y could make that solution true. So yeah, I'm just wondering why there are multiple x and y.
Sure. So here we let x be 2 and y be negative 1, right? Can someone think of another solution that also works? X is equal to negative 3 and y is equal to 2 also works, right? Because 3 times negative 3 plus 5 times 2 is equal to negative 9 plus 10 is equal to 1. Is that clear? So it's not the case that there's only one solution, x comma y. There's actually infinitely many. Okay? But it happens to be the case that all of these solutions are equivalent modulo m, right? And we see that right here. One solution was 2 comma negative 1, and the other was negative 3 comma 2. But in modulo 5, 2 and negative 3 are equivalent. So it doesn't matter which solution you end up finding because they're all equivalent. And we tend to like to represent our answers as either 0, 1, 2, 3, or 4. Remember we talked about last week when we're dealing with modulo m, every number can be written as 0, or every number is equivalent to one of 0, 1, 2, 3, ... all the way until m minus 1. So in this case, the answer we prefer to give is 2. But negative, if you find the ordered pair negative 3 comma 2, that just as well gives you the answer. You just have to add 5 until you get 2. Right? So there will be infinitely many solutions. They're all equivalent, though. Good question. Any other questions with this? Okay, so let's get into it. So again, the goal is to find integer solutions. And so we present this idea of the Euclidean algorithm. So has everyone seen this in 61A? Because I feel like they've gone over it in that class, right? Okay, maybe you haven't at this point. Maybe they just decided to not cover it. Either way, it doesn't really matter, okay? So this is another way of calculating the greatest common divisor of two numbers, okay? We saw the other way that involved taking every exponential base, right? And taking the min of each possible exponent. But this is one way that you can do it recursively with code, okay? So the GCD of A and B, and this assumes that A is greater than B, it returns the GCD of B, comma, A mod B. And it does this recursively until the B term is equal to 0, and then it returns A. Okay, so we won't talk about why this is true at this time, but let's just assume that it holds for now. Okay? So what I want to do is look at finding the greatest common divisor between 26 and 15 using this algorithm. Okay? And we know that the greatest common divisor of 26 and 15 should be 1, right? Because 26 is 2 times 13, 15 is 3 times 5. None of those are in common. So the greatest common divisor will be 1. Okay? The reason I chose 26 and 15 as opposed to something like, 26 and 12 is because when we're finding the inverse, the GCD of the two numbers we're finding the inverse of will always be what? 1, right? Because for the inverse to exist, the GCD has to be 1. Okay, so it doesn't really make sense to look at an example where the GCD is not 1. So that's why I chose 26. Okay, so if we follow this recursive call, I move 15 over to the front, and what's 26 modulo 15? 11, right? And then I move 11 to the front. What's 15 modulo 11? 4, right? Because the remainder when you divide 15 by 11 is 4. And I keep doing that. I replace the 11 with a 4. What's 11 modulo 4? It's 3, right? Because the remainder when you divide 11 by 4 is 3. And I do that, so on and so forth, until I get a 0 in the second argument, which tells me the GCD is 1. Okay, Apple Pencil died. That's fine. Are there any questions with this recursive sequence of calls? Yeah?
So are we going to be like on problems kind of doing that step by step?
Or
is that just where like the toolbox?
Let's wait till we get to the next slide. So exactly what I did right here, just like that itself won't be a problem, but we're about to use this in the next slide.
So we're going to use it.
Yeah, you will need to use this. So this is something that you do need to know. Any questions with this? Okay, does this work now? Cool, so we get the 1 there. And since we know that the greatest common divisor between these two numbers that we're going to look at will always be 1, we will always have some term of the form GCD 1, 0. Is that clear? And we'll also always have some term of the form GCD of something, 1. It doesn't matter what that something is. But we know that term will be there. Because in order for there to be a 1, 0, there has to be a something, 1, by the way that this recursive call is defined. Is that clear? So is everyone okay with why there will always be a call of the form 1, 0, and as a result, there will always be a call of the form n, 1? Any questions with this? Okay? So how can we use all of this to find the inverse? Okay? Sure, this is all nice, but how does this help us? Okay? So what we will do is for each of these function calls, we will use the division algorithm, which tells us we can, when we were trying to divide some integer n by a divisor d, we can always write n as divisor times quotient plus remainder. Does this sound familiar from last week? Right, this is the division algorithm. Okay? At each of the steps of the function call, we can use the division algorithm to write out the relationship between the first argument and the second argument. Okay? So for GCD of 26 and 15, we know we can write 26 as 1 times 15 plus 11, right? Divisor, quotient, remainder. Is that clear? And then what we can do is we can write 15 and 11, the relationship between those two numbers, as 15 is equal to 1 times 11 plus 4. Similarly, we can write 11 as 2 times 4 plus 3, and the relationship between 4 and 3 as 4 is equal to 1 times 3 plus 1. Okay, so is everyone comfortable with coming up with equations of that form? Okay? And if you're not, you might want to review the slides from last week, because that's what the division algorithm says. You can write an integer as divisor times quotient plus remainder. And so the next step in what we call the extended Euclidean algorithm is rearranging each of these equations to be in terms of the remainder. Right? In the first one, the remainder was 11. In the second, the remainder was 4. In the third, the remainder was 3. And in the fourth, the remainder was 1. Is that clear? So what we will do is rearrange these equations to be 11 is equal to something, 4 is equal to something, 3 is equal to something, and 1 is equal to something. Is that clear? And since we know the greatest common divisor between our first argument and second argument is always going to be 1, what do you know about these equations? What do you know about these equations? since the GCD is always going to be equal to 1, there will always be an equation of the form 1 is equal to something minus something else times something else. That equation will always exist because the greatest common divisor, like we would only do this if the GCD of A and M is 1. Right? We would only try to find the inverse if the two numbers are relatively prime. So we know there will be one equation where the remainder is 1. Okay? So how can this help us in finding the inverse? Does anyone have any ideas? Well, we know the end goal is to write 1 is equal to a times x plus m times y. Okay? And notice there's this sort of pattern of where the remainders appear. Each number appears twice, right? We see 3 is both here and here. 4 is both here and here. And 11, let's use this color, is both here and here. So if I substitute the equations down, I will eventually get 1 is equal to 26 times something plus 15 times something else, which is exactly what we want. Is that clear? So let's take a look. Okay, let's try and do this on the next slide, and then I'll give you an example for you to try on your own. Okay, we start off with our equation 1 is equal to 4 minus 1 times 3. And then we had our expression for 3 as being 11 minus 2 times 4. So I plug that in here for 3, right? And I simplify that. Okay? I have 4 minus 1 times brackets 11 minus 2 times 4. Okay? And that gives me 3 times 4 minus 11. The next number I have in equation 4 is 4, right? I have 4 is equal to 15 minus 1 times 11. And I plug that in here. Right? And then that simplifies and gives me 3 times 15 minus 4 times 11. Okay? And all of these equations are just equal to 1. Right? So it might seem a little silly. Why are you not, simplifying the right-hand side? Well, we know what the right-hand side is equal to. It's equal to 1. Right? The goal is to try and write 1 as a linear combination of 26 and 15. Which is why we're not simplifying. We're using the fact that we can keep plugging in successive equations, and at the end, we'll have 26 times something plus 15 times something else will be equal to 1. Okay? In the last step, we know we have an expression for 11 where, oh my god, this keeps dying. 11 is equal to 26 minus 1 times 15. Okay? So I make that last substitution in the very last line, and once I expand out, I have that this is equal to 7 times 15 minus 4 times 26, which is exactly what I wanted to do, right? If I'm looking at the GCD of 26 and 15, I want to write 26x plus 15y is equal to 1. And that's exactly what I've done here. Is that clear? So can someone sort of summarize everything we just did? Like where these steps come from and what the result means. Sure.
So you use the Euclidean algorithm to go down to 1.
Okay.
And then you keep substituting each line into the next one. And
Right.
You have to distribute factor out of 5.
Right. And the end result is that we had 1 being written as a combination of 15 and 26. Which was our goal in the beginning. Is everyone clear on what we just did? So using the extended Euclidean algorithm, I'll give you a couple minutes. Try and determine the inverse of 9 in modulo 14. So first, let's write out the calls that we would use to the Euclidean algorithm. So we would have 14 and 9. What would be our next pair of numbers? Not 14 and 5, but 9 and 5. Right, because we replace the first term with what the old second term was. Cool. So from 14 and 9, we go to 9 and 5. Then what do we have? 5 and 4, and then 4 and 1. And we can stop at that point, because all we need is that remainder of one term. Okay? So let's write out our expressions from the division algorithm. So what can I write for 14? What's the expression I can write where 14 is the number and 9 is the divisor? Yeah.
The 14 is equal to 9 times 1 plus 5.
Sure, I'll write it as 1 times 9 plus 5, but yeah. And then what we want to do is rearrange in terms of the remainder. So I'll write this as 5 is equal to 14 minus 1 times 9. Good. What can I write relating 9 and 5? Any ideas? Yeah.
9 equals 5 times 1 plus 4.
Good. And I can rearrange in terms of the remainder to get 4 is equal to 9 minus 1 times 5. Relating 5 and 4. What's the expression I can write relating 5 and 4? Any ideas? Yeah. Good, and that gives you 1 is equal to 5 minus 1 times 4. Okay, and once we get that equation, 1 is equal to something, that's when we can stop, right? Because we know our end goal is to rewrite, is to find coefficients such that we can write 9x plus 14y is equal to 1. And we start with that equal to 1 at the very end. Yeah.
So like for the first equation, when it's 14 is 1 times 9 plus 5.
Yeah.
And I see like for the following, it's always 1 times.
Yeah.
In what instance would it be like greater than this? Is that value?
Oh, it's not always. Like suppose I chose the inverse of 9 in mod 28. Right? Then it would be 28 is equal to 3 times 9 plus 1. Yeah. So it's not always 1.
Okay.
This example, they all happen to be 1, but you can't assume that these will always be 1. Okay? Those won't always be 1. That's just a coincidence in this case. Is that okay? Cool. So now first, what's our first step? What's our first move? Yeah.
You plug in your equation for 4.
Good. So I have 1 is equal to 5 minus 1 times 4, and I'll plug in the expression I have for 4 into this expression. So I have 1 is equal to 5 minus 1 times 9 minus 1 times 5. Okay, so it's getting a little messy, but really it's just a matter of multiplying the negative ones and making sure the sign works. So I can rewrite this as, I believe, 2 times 5 minus 9. Does that look right? Yep. Okay, because I have negative 1 times negative 1 here, so that's positive 5, plus this other 5, and then minus the 1. Good. And now what can I do? Well, I have this expression for 5 relating 14 and 9, and I can plug that into here. Okay? So this is equal to 2 times 14 minus 1 times 9 minus 9. And I believe when you simplify, this gives you 2 times 14 minus 3 times 9. Right? Does that make sense? Well, what's 2 times 14? 28. What's 9 times 3? 27. You subtract the 2, you get 1. So that works. Yeah.
You don't write that 2 times 5 minus 9, like from the left side of the equation.
Yeah, like how I simplified this, like this right here. Yeah, sure. So let's do that over here. So I can write this as 5 minus 1 times 9 plus, I guess I can write it as this, minus negative 1 times positive 5. Is that clear? So I'm just distributing the negative 1. Okay? And what's negative 1 times 5? Well, that's just negative 5. So I have 5 minus 9 minus negative 5. Well, that's just 2 5s minus enough. Is that clear? So any questions with that stuff? Okay, so you have to make sure that you're not making any arithmetic mistakes when you're doing all this, because then you'll just end up with the wrong answer. Okay, so what does this tell us? We were able to write 1 as 2 times 14 minus 3 times 9. Okay? And what was our end goal? We wanted to write 9x plus 14y is equal to 1. And that would tell us that x is the inverse of 9 in mod 14. So here, what's the value of x? What's the value of x we found? -3, right? Because that's the coefficient on 9. So we have that -3 is the inverse of 9 in mod 14. How can we rewrite -3 as being in the set 0 to 13? Yeah.
Just add 14 to it.
Yeah, I can add 14 to it. So that gives me that 11 is the inverse of 9 in modulo 14. And so the answer we would probably look for is 11. I mean, not that -3 is wrong, but when we ask for the inverse, we usually want a number between 0 and 13 inclusive. Okay? So it's fine that we solved and got -3, but just to report the answer, we add 14 to that, because that just gives us an equivalent set of numbers. So our final result is that therefore 11 is the inverse of 9 in mod 14. Okay, can we verify that? Yeah, well, what's 11 times 9? Well, that's 99. Well, that's equivalent to 98 plus 1. And I believe 14 times 6 is 98. Right? So that gives that's equivalent to 1 mod 14. So it looks right. Yeah?
We don't care about the y.
No, so the value of y doesn't factor into the answer at all. Right? All we want to do is find this number x. In order to find x, we also need to find y. But the fact that we got y being equal to 2 doesn't really mean anything in this question. Any questions with this process? Okay? So it seems like there's a lot going on, but no matter the situation, it's always the exact same process. Okay? You write out your calls to the Euclidean algorithm, right? So in this case, we had 14 and 9, 9 and 5, 5 and 4, and 4 and 1. We write them in terms of the division algorithm and rearrange for the remainder. And then we repeatedly substitute into our equation for 1 is equal to blank. So we substitute the second last equation into the last, and then the third last equation, and so on and so forth, in reverse order. And eventually, you'll get 1 is equal to some linear combination of 9 and 14. Or in general, some linear combination of a and m. And then we take the coefficient on a, and we know that that is the inverse of a in modulo m. And that's exactly what we did here.